Okay, so this data file that we have open now in SPSS has two variables in it. I'm going to flip over very quickly to the variable view and click tab down there. And I can see represented here the first column is described in this row as a variable named height. Okay, and it's actually a numerical variable. You can see that SPSS sees it as a scale or scalar variable out of those three choices: ordinal and nominal, or categorical as we call it. And gender is indicated as a nominal variable, as it should be. It's male or female. Okay, and in this area here that says values, this column here that says values, we've gone in and we've coded. If I click in there, I get a little box here. I click on that, and it brings up value labels. It's coded so that if we put a 0 in that column, SPSS recognizes it as male. If we put a 1 in that column, SPSS recognizes it as female. Okay, most likely for this first exam, the data that I'm going to give you is going to be pre-coded, so you're not going to have to worry about this. Next time that we do this, you're going to be expected to code the data yourself, and we're going to show you how to do that. It's pretty easy. So right now, I can see height and gender, male, and if I scroll up, I can see there's quite a few people here, male and female. Okay, so now I'm gonna say to myself, well, oh well, how do we know? You may not see it exactly that way. If I'm going to click in View, and right now the value labels are checked off or turned on. If I turn them off, you see the actual value that's typed in there, 0. You don't see the translation from the value label table. So if you see this, don't get alarmed, right? You can just, if you want, turn it back on or even leave it the way it is. Okay, so if you see something a little bit different, but that'll help you distinguish which is male and which is female anyway. Okay, so now you will most likely be asked to produce some graphs and some data based on these values, these variables. Okay, and in this case, since we're dealing primarily with a numerical variable, that's going to involve descriptive statistics, things like mean, median, range, interquartile range, and so on and so forth. And we're going to go over some of the things that might actually show up that you'll be asked to do. Well, anytime we want to do this, there's two ways that we can create graphics. One way is to go into the graphs and go into the various choices that we have here. Chart Builder, which is kind of like a wizard to help you build graphs and so on and so forth. Or even just the simplest one, which is the legacy dialogues, which make it really easy for you to draw bar graphs and histograms and box plots and stuff like that. They're really pretty. It's really pretty basic. But for our first session, during our second session when we played around with SPSS, we found that we didn't really have to go into graphs at this stage because a lot of the graphics that we wanted were already calculated as part of SPSS analysis for descriptive statistics. Okay, so we're going to take advantage of that. I'm going to calculate the descriptive statistics for males and for females. Now, I just want to point out that anytime I want to do an analysis, I just go up to Analyze, and I can choose from this drop menu. We're going to want descriptive statistics. Descriptive statistics frequencies is just going to do counts, the number of males and the number of females, for instance. Okay, that's not really much use to us. Besides, other calculations, other analyses will do that automatically anyway. The second choice, descriptives, seems like a tempting choice here, and I'm going to pick it for the moment. And in fact, I can see it comes up, asks me what variable that we want to find the descriptive statistics of. Okay, now I don't want to move gender in there because gender is male and female. I don't want to find a mean standard deviation for male and female. It doesn't make any sense. I want to find it for the height of the student. So I would only move the numerical or scalar variable in there. Okay, and then I would go ahead and do the calculations. An output window would open up and it would find the minimum, maximum, mean, and standard deviation, and that's it. By the way, it does count as well. Notice the count counts all the students. It doesn't count male and female. So although this gives us some information, it's not really what we were after. We want to know male and female average heights. In order to do that, we are going to go into Analyze, and we're going to take the next choice, which is Explore. Analyze, Descriptive Statistics, Explore. Okay, and I'm going to, now it's going to ask me now, notice there's more boxes that have opened up now. And we have more choices here. We have a lot more opportunity to do things here. Okay, so the first thing it's going to ask me is the dependence list. That's going to be the variable that I want to find the descriptive statistics for. Again, gender wouldn't be the right choice there, would it? Because we don't want to find descriptive statistics for males and females. We want to find it for the heights. Okay, now we want to divide those heights up into two groups: male statistics for males and statistics for females. That's where we're going to put gender, because gender is going to be our factor list. You remember when you took math earlier, if you're going to take the number 10 and they ask you to factor it, you would factor it into 5 times 2. You would break it up into two parts. Okay, this is what they mean by factor. Break it up into whatever these variables are. Had this been hair color, and there would have been 5 different hair colors listed, well then it would have broken it up on height of people by different hair color. Okay, whatever this factor, it's got to be a nominal. It's going to be nominal, right? This is going to be scalar. So if you get this reversed, it's not going to work out very well for you, and you'll know immediately that something's wrong. Okay, so if that happens to you, just go back and reverse them. If you forget this, and just go back and reverse them. Okay, so right now, we've chosen to display both statistics and plots and graphs as well. Okay, rather than just one or the other. But now we're going to go in here. And we're going to take a look at these options that we have. I'm going to click on statistics. It's already checked off to calculate descriptive statistics. If that's empty, it won't calculate the descriptive statistics. So if you see that empty, just go ahead and check it off. By default, it'll be checked off, so most likely you won't have to do anything there. Under plots, well, right now, when Explorer does the descriptive statistics, it automatically produces a box plot, so we don't have to check that off here anywhere. But it doesn't automatically produce a stem and leaf plot or a histogram. Okay, so I'm going to make sure both of those are checked off so we get them as well. Okay, so I'm going to click continue. And now in options, this deals with like if you have missing values and stuff like that. I wouldn't be too worried about that for our exam this time. So now I'm just going to click OK. The output window will come up. Okay, and notice how much more information we have now from SPSS. We now have all sorts of information about the number of cases, percentage of each one in each group. We have male, standard deviations, variance, so on and so forth, for broken up for males and for females. You see, average female height is shorter than average male height. We have the median for male heights. We have the median for female heights. We have all that information that we might be asked to provide on an exam. We have a histogram, a bar chart for male heights, 66 inches, 66 and a half, 67, so on and so forth. Okay, it actually throws in a few statistics there as well. We have the distribution for females. One of the things we might look at is, do these look like they're normally distributed? And these actually look like they're skewed a little bit to the left. There were a couple of very tall females in this particular group, it looks like. And with males, it looks, I guess it's pretty normally distributed. Maybe there's a couple of unusually short males in here. Okay, so now stem and leaf plot is just a representation of each of the values: 65 inches, 66 and a half, 66 inches. It's one person, 66 and a half. A representation of this distribution non-graphically using ASCII text. Okay, and you'll notice that it's very much the same shapes as we saw up there. Okay, now here's our box plots. And our box plots, as a reminder, these box plots give us a lot of information. These leaves that go down here, the bottom leaf represents the minimum value. The top leaf represents the maximum value. The black bar in the middle represents the median or middle value. And the outskirts of this box, the bottom of it represents the 25th percentile. In other words, 25% of the group is below this. 25% is between here and the median. 25% is between here and the 75th percentile, the top of the box. And the other 25% is between here and the very highest value, the very tallest person. And this value for females, we can see pretty clearly that in general, female heights are shorter than male heights. Okay, we have a couple of very tall females. Remember I mentioned that to you? SPSS decided that these were so far from the median, or from the 75th percentile, that it was going to draw the maximum value here and display them as a dot representing outliers or values that you should investigate that maybe there was some problem with the measurement or something else like that you might want to not consider using with the other data, right? But we'll get into that as we go on. Okay, so now I'm going to ask you a quick question. This median here, right? This median is over here, and there's values that are dragging it away up the rest of the group away up here, away from the median. So the median is not in the middle. What does that suggest to you when the median is not in the middle of the box plot? Well, outliers, yeah, but another thing about outliers is what are the outliers? What are very tall people going to do to the average? The very tall people are going to pull the average up, but they're going to leave the median behind. So this represents a skewed distribution, right? And which direction is it skewed? It's skewed towards the higher numbers. In other words, there's people pulling the distribution higher, right? So it's skewing the distribution to the right or positively or to the higher numbers. If I go back to the females, remember the female population? Here's our normal distribution. We would expect it to look kind of like this. And then see those guys that are outside of there, they're pulling the average to the right or positively. It's not that dramatic here. I mean, if these guys were out here, it would be a little bit more dramatic. But you can see that the median stays here, but when you get people that are way up here, it tends to pull the mean away from the median to the right or positively. Had these guys been on this end, it would have been a negative skew. And when we looked at the box plot might have been, see, there's a little bit of a negative skew here because the median is a little bit high, but it's pretty much actually it's a lot closer to the middle than the female values are. So I wouldn't really kind of describe that as skew. Okay, this one would be skewed to the left if anything. It's really not skewed much at all, but to the left, if anything. And this one is skewed to the right or to the positive numbers or bigger numbers. Okay, okay. Zanetta, did you get that? Yes. Okay, good. All right, good. So that's now the only other thing about this that I'm going to want you to practice a bit is that it's nice for this stuff to be in uh, in uh, 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 in an SPSS output table. But that's useless to you. You're going to want to dazzle people in the future with your reports and your skill using statistics. So it's important to you, and I don't do this to torture you. I do this because I know it's going to be valuable to you in the future. It's one of those skills that's going to make a difference. Okay, we can copy any of this material that's in this output window for SPSS into other applications, including Word. For instance, if I want to copy this table, this box plot, I just highlight it. I'm going to say copy, okay, and then I'm going to go to Microsoft Word, okay, and I've opened a document here, and I might be writing a report and so on and so forth. Now might want to insert that box plot. I'm going to go here to insert, to paste. Now I have two choices whenever I paste. I can paste or I can paste special. When you're using a version of Word that's using the ribbon, you'll see paste as a little object on the left-hand side or the right-hand side of the ribbon. If you just click right on that thing, it'll just paste it in. If you click on the little arrow below it, you'll also get a choice just like here that says paste special. And when you get a choice that says paste special, it gives you some additional options for pasting. In this case, it's just going to say picture because we're copying a picture, a chart, out of SPSS and we're putting it into Word. Okay, so now this is available for us to use in here to move around to different parts of the document and so on and so forth. If I click on it, I can even center it and so on and so forth. Up, maybe not. Should let me center it. I guess not. Okay, so I'm gonna move this up here a little bit. Okay, I'll move that in there. Okay, and I'm going to move down here. You can move this around any way you want, like work with it and stuff. But okay, so now I'm going to go back and I'm going to take a look at, let me go to the output window. I'm going to take a look at this table that we've produced here. This table with the means and the medians and so on and so forth. I'm going to copy, I highlighted that. Notice how it's highlighted. You see a thin little line around it, a red bar. I'm going to say copy. Now, in this case, I have two choices. Okay, when I go back to Microsoft Word, okay, my choice now is I'm going to go to edit and paste special. My choices now are many: formatted text, unformatted text, so on and so forth. If I click formatted text, it's going to paste it in there as a regular table. Okay, so now I can actually go in and edit this. Notice all the markings up here on the bar that show you the tabs and where the columns are and so on and so forth. The only problem with this is that it's bigger and wider than the actual paper I have is that's displayed. And in order to adjust it all, it's going to be very tedious for me to narrow this portion and so on and so forth. One of the things that you can do instead of this, I'm going to undo paste, is that when you say paste special, you can choose instead to paste it in as a picture. When you paste it in as a picture, it'll do two things for you. Number one, I'm going to click here. It's going to paste it in a size picture size that'll fit within the margins of the paper that you're working with. And the second thing is it's going to make it a lot easier to resize it and to move it around the document than that table. Now it's up to you which way you want to do it, but when you're going to be doing a very simple, I'm going to give you a data set very similar to this, ask you to do descriptive statistics, maybe ask you a couple of questions about it, ask you to provide a box plot, and a histogram or something like that. But I'm going to ask you to put it into a Word document, and then you're going to email it to me basically, or upload it to somewhere on Blackboard, depending on what's working better that day, tomorrow night in the Monday night in the exam room. So we're going to take a look at that, so that you'll have the skills to do this later on when you have to do a report, rather than just give me an SPSS file. One of the other things is not everybody's running version 19 or 20 of SPSS. If you're giving an SPSS output file to someone that's running an older version of it, they may not be able to open it. Okay, so and not have that data at all. Okay, so that's, you can expect to be able to do something like this example, very similar to this example. I think by this time most of you guys will be able to get through this. Okay, and don't get flummoxed. I mean, it's you can't do anything to break SPSS or the data file. So uh, uh, I don't think you'll have too much of a problem with it. Okay, let me see what's the right. When it's the right, that's the higher numbers. Yes, I'm answering a question from before. Are you guys pretty comfortable with SPSS? Can we move on from that? Okay, good. All right, good. Now let's go back to that list we started before. Let me get all this stuff out of the way. Okay, histogram, box plot, stem and leaf plot. We just talked about that a bit. Know how to approximately calculate the median, mean, quartile, percentile, and other quantities. We did that in SPSS, but remember we also went through calculations like that in Excel, and also remember that we also did this kind of thing when we were looking at the histograms. We did counts to find the median. We did counts to figure out what the percentiles were and stuff like that. Know how to judge whether the distribution is skewed or not from the histogram or box plot. We just talked about that. Pie chart and bar graph. We know how to interpret that. The only thing that's a little bit different in pie chart is that in the pie chart, if we were looking at the grades that we were just discussing in a pie chart, then each of the grades A, B, C, D, A, B, C, D, F would be represented by a proportion of that pie chart, a section of that pie chart. So you would be able to do the same thing, say, for instance, for a conditional probability, what percentage of people that got above they got above C, or got A's. Well, then you would know only to start with the areas of the people that got A, B's, and C's, and then figure out what percentage of those that area were A's. So you exclude the D's and F's from your calculation. Okay, so that's really the only difference with a pie chart. know how to calculate proportions, conditional distributions, given a pie chart. Well, we just talked about that right now. Give a list of quantitative values you can calculate, but okay, so in other words, this might be given a list of numbers, like 10 numbers, that you can calculate the mean, the median, the interquartile range, the sample variance, and the standard variance. I think there's actually one of the videos up from one of the labs where we actually did this. But you guys recall that we calculated mean by adding up all the numbers, dividing by the sample size to get the mean. The median is the middle value. So, and if there's an even number of values, like 10 people, then it would be the average of the fifth and sixth value, the middle two values. Okay, the interquartile range. Well, that would be start from the median, the middle, and go half on the bottom half, find which number is in the middle of the bottom half, and which number is in the middle of the top half, and the difference between those two numbers would be your interquartile range. Sample variance. Remember, add up the differences between each value and the mean, square each value, square each one of those values, add up the sum of those squares of the differences, and divide by n minus 1, and that gives you the sample variance. Then take the square root of the sample variance, and that gives you the standard deviation. Or I guess that's he called it standard variance, but he means standard deviation. Give a list of categorical values you can calculate. You can calculate the proportion, okay, like the bar chart that we just have. The number of redheads, brunettes, blondes, and so on and so forth. What's the probability of picking out a blonde from this population that had 10 redheads, 3 blondes, 14 brunettes, and so on and so forth? Similar to what we just talked about. Distribution. For discrete or categorical variables, a table of bar charts, or know how to calculate the proportions again. Now, skewness. Skewness is, that's kind of interesting. Skewness is a little bit of a complicated calculation. I don't remember if that came up. Maybe he's saying that he wants you to identify skewness rather than actually calculate it. There is a formula for calculating skewness. If it comes up, I'll send out I'm going to check on that, see if he really wants you to calculate that. If he does, then maybe I'll send out an email later on. Okay. For a 2 by 2, okay, continuous variables. Okay, for a 2 by 2 table, okay, or 3 by 5 or whatever. Know the marginal probabilities, how to verify 2. Okay, now when we say 2 by 2 table, we're talking about, say, something like an exposure and an outcome. Those 2 by 2 crosstab tables that we've started dealing with that are going to come up quite a bit. Um, uh, 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 there's going to be various probabilities that you can calculate based on those. For instance, let's say the rows are exposure to, let's say the top row is exposure to asbestos, bottom row is no exposure to asbestos. And the columns represent, in the left column, cancer, the right column, no cancer. Okay, so the top right hand corner would be a person that was exposed to asbestos that got cancer. So if that has a number like 300 in it, 300 people in this study were exposed to asbestos and got cancer. If the number below that, no exposure to asbestos, and that number was 1,000, then you would know 1,000 people were not exposed. Excuse me. Let me change that. Say 100, you would know that, say, 100 people not exposed to asbestos got cancer. So the total number of people that got cancer was 400, 300 exposed, 100 not exposed. So if you want to know what the probability uh, 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 in that study of being a person that has cancer, what's the probability if you have cancer that you were exposed to asbestos? It would be 300 over 400. You could go through almost every permutation of those boxes to figure out, probability of getting disease in different categories, probability of exposure in different categories, and so on and so forth. But you can play around with that. It should be pretty intuitive, I think. No, how to know verify two variables are independent. Well, let's take an example of that. If I told you the probability of having probability in this study of having diabetes is in a population is 10%, and I told you the probability of being female in that population is 50%. Okay, I might ask you, what's the probability of randomly picking a person that out of a population that is both female and has diabetes? Okay, well, you would say probability being having they're independent. If they're independent events, one doesn't influence the other. So the probability, let me just kill that. The probability of being female is zero point 0.5 times the probability of being diabetic is 0.1. So the probability of being both is 0.05 or 5%. Well, now let's say we do a study, and that study tells us, well, we did a study, we found that 6% of the females in this study were diabetic. Well, what does that tell you? That tells you that those two events are not independent. Being female influences the probability of having diabetes. It makes it more likely since it's higher than it would be if they were independent events. So the key here is to look at the probabilities of each of the two outcomes independently. And if they don't multiply out if you multiply them together, if they're not equal to what your study shows, then you know the two events are not independent. Okay, does that make sense to you guys? Anybody out there? Are you guys okay with that? You have a question on that? I don't see any response. Okay, I'll move on. Okay, table represents diagnostic test. Oh, okay, you're gonna have to work through that the sensitivity. Thanks. I got some responses finally on that. Okay. The diagnostic testing. We're not going to have much time for that right now, but I think we went through that pretty thoroughly on the last video that's up. If you need some, if you still think you need a little bit of help on that, send me an email. Maybe I'll post something else up on that. That's from the previous lab session. I think we have some videos up. Um, Normal distribution, cumulative probabilities, how to calculate them. That's a z-score and so on and so forth. Know how to calculate probability. What he's saying there is know how to calculate the probability between two different outcomes, two different z-scores. And we looked at that in terms of how we could use the empirical formula and how we could use the z-table to calculate areas and then find and then use our knowledge, the fact that the normal distribution is symmetrical, and our knowledge of the probability being adding up to 100% for the entire distribution, using that knowledge to figure out what the other areas are that the z-table didn't tell us. Know how to derive the z-score and use it for comparisons. Now, that's interesting. He brought that up a couple of times. So one thing I learned as a student, if a professor brings something up a couple of times, that it's probably important. And let's talk about this. Comparing the relative heights of a woman and a man. Okay, I'm going to pull up a sheet of paper, an Excel spreadsheet, because I don't have a tablet attached to this thing. Okay, let's say that the average male, the mean height for males is 58 inches. Let's say the mean height, I'm going to male. Okay, mean height for females is 54 inches. Okay, let's say I get Wendy and Sal come in, and both of them are 56 inches tall. Well, on an absolute basis, I'm going to say that the standard deviation for both of these is 2, right? For males and females, they have the same standard deviation, same spread. They just have 2 different means. Okay. On a empirical base, and if we just looked at them independently, we would say these two people are the same height. However, that doesn't make a lot of sense, does it? Because it's hard to compare male and female heights because they're really from two different populations. And what we might notice is that, well, gee, Wendy is 56 inches tall. The mean female height is 56 inches tall. She's 2 inches taller than the mean female height, right? What does that mean? That means that she's one standard deviation above the average female height, right? Plus one standard deviation. What does that tell us? Whoops. Plus one standard deviation above the female height. Okay, what does that tell us? That tells us that Wendy is in the top 16% of height for females, doesn't it? Because we know that the rule is one standard deviation below and above is 68%. That means 34% is in the top half. 34% of one standard deviation represents 34% of the top half, and that leaves 16%. She's in the top 16%, as we saw before. On the other hand, Sal is in the lower portion of this. He's one standard deviation below the mean for his population. He's in the lower 16%. So, relative to each other, they're the same height. But relative to the populations that they represent, one is unusually tall, one is unusually short. I'm pretty sure that that's what he's after. So, be prepared to, deal with a question like that if it comes up. He's mentioned it a couple of times, as I said, Professor Yang. How to derive z-score, comparing heights and relative heights, man and woman, as we just did. Binomial distribution, know the definition, how to calculate it. He just, I didn't do this on purpose. He just, actually, I used zero point 0.4. He's using 0.5 here. He used a very similar situation. I would expect the numbers are going to be small like this or simple like this on if he gave it to you on exam, because the expectation is that in order for you to work it through using a simple calculator and the time you have, it's going to make it hard to give you a very complicated one. Know how to calculate the probability of certain events, seeing three or four patients out of 5 people, so on and so forth. So yeah, we just that's binomial distribution, and we just discussed how to use that formula to calculate that. Okay, so 3 out of 4 would be n would be 4. 3 would be the outcomes. The outcome and the probability p would be 0.05. Basically, same problem he's describing there, except as a word. Okay, so now we can either end right now. Oh, let me just see the questions here. That's a good question. I think probably he will be asking you a few definitions. There might be some material like that. If you have the textbook or the PowerPoints or your notes with you, I think that most likely any definition he would ask you would be probably in the PowerPoints, and almost definitely, you could use the index in the book to, to dig it out if you needed to, if you needed a technical definition. Okay, and let me see. The definitions. I lost one of the questions there. Did I delete one of the questions accidentally? I lost that last question. Whoever put up that last question, I think I just lost it. So if you want to put it up again, I'll address it. Okay, so do you guys want to spend 5 more minutes and take a quick look at what we just skipped over, which was the diagnostic tests? Do I have a yes or no? Yeah, you're gonna have the 2 hours or the hour and 50 minutes for the written portion of it, and you'll have the an hour for the lab portion of it. And trust me, on the lab portion, it won't take anywhere near that long. Okay, so are you guys interested in quickly going over it? Yeah, I hear, sir. Yes. Okay. If we need extra time, we're kind of nailed in because in the lab session, I can't give the guys in the early session extra time, so it wouldn't be fair to give extra time late people. And both of you are nailed into the 2 hours on the test for the middle section, so you have to trust us to be reasonable. I know that it's hard to trust professors to be reasonable, But you'll be given a you'll be given a Z table of some form, yes. And but it wouldn't hurt that if you have the if you bring in a textbook, you got the Agresti one in there, which I like the Agresti one because it's very simple. You don't have to worry about left, right side of the distribution, positive, negative Z-score. It really works it out for you. You know everything. That area is going to be everything to the left of whatever it says in that graph of that chart. So it happens to be an easy one. Most of them are only give you one side, and you have to deduce what the percentage on the other side is. Okay, let's do a quick look at diagnostic tests. Okay, I'm gonna put in here. Let's see, cancer. We got developing a new screening test for cancer. No cancer. Okay, and the test is positive, or the test might be negative. Okay, and in this study, we examined, say, 1,000 people, and we took a sample of 100 people who had cancer. We took a sample that left 900 people that didn't have cancer. We might have actually gone for two groups that were similar, except for whether they had cancer or not. So it might not be necessarily the prevalence in the population, but this is the way the study shook out. Let me center this so that it's easy to work with. Okay, so let's say in our screening test that out of the 100 people that had cancer, 80 of them were tested positive, 20 of them tested negative. Of the 900 people that didn't have cancer, let's say that 890 tested negative and 10 tested positive. Okay, so let's see what this test tells us. First of all, what is the sensitivity? Sensitivity. What's the sensitivity of this test? Anybody want to hazard a guess? Okay, give me a formula that you might work out with. Okay, everybody just threw out 80%. Of course, the sensitivity is equal to the how good it is at identifying people that have cancer. 80 out of 100 people. It properly identified cancer in 80 out of 100 people. So the sensitivity is equal to the number of true positives, 80, over the number of people that actually have the disease, people that are disease plus, which is 100. Okay, so now what's the specificity? The specificity is the same deal except for a negative test. How good was it at identifying the 900 people that didn't have cancer? Well, it got it right 890 times. In other words, true negatives over the total number of people that were negative. So that's equal to 890 divided by 900. Okay, so now almost 99% specificity. Now let's take a look at one of the things that's really important here is, okay, you got a positive test. How good is that at identifying you as a person who has the disease? Now you have cancer. If you have a diagnosis of cancer, a test tells you have cancer. Chances are the next thing they're going to do is going to be a definitive test, a reliable standard. Let's say this was a blood test, more reliable standard like a biopsy, an invasive procedure. So you don't want to have a positive test unless you really have it, because the next step of diagnosis is invasive. Okay, so what's the positive predictive value? How predictive is a positive test in this case? Okay, so first thing we got to figure out is how many people actually tested positive. 90 people actually tested positive, and that means that 910 people tested negative. Okay, out of those people that tested positive, those are all the people that tested positive. How many of them actually have cancer? So we're interested in, what are we interested in? We're interested in the number of people that actually have cancer divided by the total number of people that tested positive. So if you tested positive, there's an 89% probability that you actually have cancer. That's a pretty good test, most likely. Okay, now I'm going to ask you, you tell me what the negative predictive value is. If you tested negative, 900 people tested negative, what's the probability that they're really negative? What should I divide by what? Don't bail out on me now. We're almost at the finish line here. Okay, we got, oh, great. Okay, we're going to divide 8, 9. Oh, hang on a second. We're interested in this. There's 910 people that tested negative. 890 of them were actually negative. So the negative predictive value is it got it right 890 times out of 910 that tested negative. Right? So that's a negative predictive value of 98%. 2% of the time, it said people were negative when they weren't negative. Okay, so but these are pretty good results for this. Now, this is a population where the incidence. This is a group where 10% of the population was uh, was uh, was excuse me had the disease. Right. Let's change it to a situation where 1% of the population has the disease, just for the hell of it. Okay, so specificity and sensitivity is still the same. I didn't change anything there. I just changed the number of people that had the disease. Still 8 out of 10 or 80% of the time it got it right, and so on and so forth. This time, notice what happened to the positive predictive value. The positive predictive value went way down, way down. Okay, now I didn't adjust this. Hang on a second. I got to adjust this. So 900. No, let's see, 900. No, this would be 990. That's where I got. That's where I'm wrong here. So 990. So 80%. So I'm not going to bother with the negative, but you can see the positive predictive value went way down. Okay, if we got this chart, you'd be given this chart. You might be given two versions of it. One with a high a high incidence, one with a lower incidence. But that's the kind of thing that might come up. Yeah, 908. Okay, I'm going to skip it for now, but uh, uh, rather than go back over this because I want to cut this off so I know that it's going to record. Okay, guys, so good luck on the exam. I'm going to post answers for homework 3 and 4, and I'm going to post selected answers for homework number 5 so that you still get a chance to, like I'll solve a couple of them for you, but it'll still give you a few that you can do for submission the following week. And so good luck on the exam. And like I said, so email me if you have more questions, and I'll be happy to reply to your emails. Take care, guys. Bye.